An example of a system is given below and it is required to check if it is deadlocked or not. Process A holds R, wants S. Process B holds nothing, wants T. Process C holds nothing, wants S. Process D holds U, wants S and T. Process E holds T, wants V. Process F holds V and wants S. Process G holds V, wants U. This is the corresponding resource allocation graph. And in that one, here there is a cycle. In part B, we have cycle extracted from A here. Because we have single instance of each resource and there is a cycle, there is a deadlock in the system. However, if there are more than one instances, then it will become more complicated. If there is a single instance of each resource in the system, then an algorithm for finding a cycle in a graph may be used to understand if there is a deadlock or not in the system. However, if we have multiple instances of each resource type, then in that case, we need a more complicated algorithm. A version of the Banker's algorithm may be used for this purpose. The required data structure is as follows. We have available M, allocation NM, request NM, same as in the Banker's algorithm. And also we have work and finish vectors of length M and N as in the safety algorithm used in the Banker's algorithm. The algorithm is as follows. 1. Initialize work as available for I from 1 to n if allocation I is 0, row vector is equal to 0 vector, then finish I is true. That means that if nothing is allocated to a process, it cannot take part in deadlock. As finish I is set as false. In other case, we have to check if it is able to finish or not. Step 2. Search an I such that finish I is false, it is not found as to terminate yet, and request I less than equal to work. If no such I can be found, go to step 4. For I found in step 2 here, do work is equal to work plus allocation I, finish I is true. And go to step 2. Step 4. We may come here either because all finish values are true or some of are false, but for those processes having value false, it is not satisfying. Request I is less than equal to work. If finish I is not equal to true for some I, then the system is in deadlock state. As if all of them are true, there is no deadlock. Consider this graph. We have 4 processes and 3 types of resources. R1 and R2 are single instance and resource type R3 has 2 instances. Because all of the processes is allocated at least one resource, we have finish values are false for each of them. If we compare to the safety algorithm, the only difference is this part here. If a process is not allocated any resource, in that case, the corresponding value will be true. The rest of the algorithm is the same. For this graph, we have no free resource, so available is 0 for all of the resource types. And the allocation is as follows. For process P1, R1 is allocated, we have one here, and it is not allocated any of the other resources. They are 0. For process P2, R2 is allocated, we have one here, and no more resources allocated to process P1, so we have 0 here in these entries. For process 3, R3 is assigned. We have one here. And for process 4, R3 is assigned also. We have 0, 0, 1 for process 3. And the requests are as follows. Here we have process P1 requesting R2 and R3. So we have 1 and 1 for the columns R2 and R3 for the process P1. For process P2, it is requesting only R3, so we have 1 here, and all the other entries are 0. For process 3, it is requesting R1, we have 1 here, and the other entries are 0. And process 4 is not requesting any resource. So we have available allocation and request. As we have found previously, all the finish values are false and work is set to available. We are trying to find a row here which has entries less than or equal to work. And if we check all of them, for these 3 processes, it is not satisfied. However, for process 4, request 4 is less than equal to work. So we are setting the value I as 4 and work is set as work plus allocation 4. So process I is able to terminate and work is set as work plus allocation 4. Allocation 4 is this value. This is added to work. So work will become 0, 0, 1. And we are going to set the value of finish for process 4 to true. Then we will have true here. And work is 0, 0, 1. And this was the allocation and request. Then we are trying to find a row for which the value is less than equal to work. Check this process P1, it is not satisfying the condition. However, process 2 has request 0, 0, 1 and it is less than equal to work. So we are setting I as 2. And then we are setting work as work plus allocation 2. So it is 0, 0, 1 plus 0, 1, 0. So it becomes 0, 1, 1. And also finish 2 is going to be set to true. Therefore, we have work as 0, 1, 1. And here the value for finish 2 is also true. Now find a process for which finish value is false. Here we have process P1 and P2 for which finish values are false. And for those processes, we have to check if request is less than equal to work. Let's start with process 1. It has request 0, 1, 1 and it is satisfying the condition. Request 1 is less than equal to work. So we are setting I to 1. And we are setting work to work plus allocation 1, 0, 1, 1 plus allocation 1 is 1, 0, 0. Here work becomes 1, 1, 1. And finish 1 is set as true. This is going to be set as true. So we have work as 1, 1, 1 and the value here is true. Then we have only this process having finish value as false and we are checking if this request is less than equal to work, it is satisfied. So I is equal to 3. Work is equal to work plus allocation 3, which is 0, 0, 1. So we have 1, 1, 1 plus 0, 0, 1. The result is 1, 1, 2. Now the new value for work is 1, 1, 2. And also the finish value for process 3 is going to be set to true. And these are the new values for work and finish. Here we are trying to find a process for which the finish value is false. There is no such a process. Since finish I is true for all I, there is no deadlock in the system. We go to step 4. And we understand that there is no deadlock because all the finish values are true. Recovery from deadlock. Possible methods of recovery, though none are attractive, are preemption, rollback, and killing process. If the system is in a deadlock state, some methods for recovering it from the deadlock state should be applied. There are various ways for recovery. One of them is allocate one resource to several processes by violating mutual exclusion. This seems not to be applied for all the resources. And another one, preempt some resources from some of the deadlock processes or abort one or more processes in order to break the deadlock. If preemption is used, then select a victim. However, we have the question, which resources is or are to be preempted from which processes? Rollback. If we preempt a resource, we have to check the cost of the rollback. If we preempt a resource from a process, roll the process back to some safe state and make it continue. It may not be possible for some of the resources. Here, operating system may probably encounters starvation problem. How can we guarantee that resources will not always be preempted from the same process? In selecting a victim, important parameters may be, for example, process priorities, how long the process has occupied the resource, how long will it occupy the resource to finish its job, how long will it occupy the resource to finish its job, what type and what amount of resources did the process use, how many more resources does the process need to finish its job, how many processes will be rolled back. In this case, more than one victim should be selected. For rollback, the simplest solution is a total rollback. A better solution is to roll the victim back only as far as it is necessary to break the deadlock. However, the operating system needs to keep more information about process states to use the second solution. To avoid starvation, ensure that a process can be picked as a victim for only a small number of times. So, it is wise idea to include the number of rollbacks as a parameter. Another kind of deadlock can occur in communication systems, for example, connection networks, in which two or more processes communicate by sending messages. A common arrangement is that process A sends a request message to process B and then blocks until B sends back a reply message. Suppose that the request message gets lost. A is blocked waiting for the reply. B is blocked waiting for a request asking it to do something. Communication deadlocks cannot be prevented by ordering the resources since there are no resources, or they cannot be avoided by careful scheduling since there are no moments when a request could be postponed. Fortunately, there is another technique that can usually be employed to break communication deadlocks. It is timeouts. Suppose that we have 4 hosts and we have routers A, B, C, and D, and inside the routers we have buffers. This is showing a resource deadlock in a network. When a packet comes into router from one of its hosts, it is put into a buffer for subsequent transmission to another router and then to another until it gets to the destination. These buffers are resources and there are a finite number of them. Suppose that all the packets at router A need to go to B and all the packets at B need to go to C and all the packets at C need go to D and all the packets at D need go to A. No packet can move because there is no buffer at the other end. And we have a classical resource deadlock, albeit in the middle of a communication system. Here in this figure, a busy waiting that can lead to Livelock is shown. This is process A, acquire lock on resource 1, while try lock resource 2 failed. Do these steps, release lock resource 1, wait fixed time, acquire lock on resource 1. So, while trying lock on resource 2 fails, it is releasing resource 1 and waiting for a fixed time and then requiring resource 1 back. Use both resources when it gets out of the loop because resource 2 is available. This is not failed then. Use both resources, release lock on resource 2 and release lock on resource 1. And the code for process B is the same except that it is first requesting resource 2 and then trying to lock resource 1. If the concurrent execution of the processes are such that process A acquire lock on resource 1, then process B acquire lock on resource 2, then process A apply try lock on resource 2. It will wait here until process B release the resource, but it will not be possible because here in this step process B is applying try lock on resource 1, which is held by process A. So they will execute this step forever. There's a busy waiting, so this is causing Livelock. So they will never be able to terminate. Livelock and deadlock can occur in surprising ways. In some systems, the total number of processes allowed is determined by the number of entries in the process table. Thus, process table slots are finite resources. If a fork fails, because the table is full, a reasonable approach for the program doing the fork is to wait a random time and try again.